Right, so last time we were in the middle of proving this theorem. Let me go over the statement and what we've proved so far. Let G be a cyclic group with n elements and generated by an element T, right? Which is what's given over here. Then we take an element B in G, and because BG is generated by A, B has to be some power of A. So we'll take it to be A to the power of S. Then B generates another cyclic subgroup H of G containing n over D elements, where D is the greatest common divisor of n and S, right? So now, and then if AS generates, if the greatest common divisor of n and S is the same as the greatest common divisor of n and T, then the element that generates the subgroup AS is also generated by AT. A to the power of T, that is. Right. So far, we have shown this, right? Now, we have taken the order of B to be M, right? Since H is generated by B, all we've got to do is show that M is equal to N over D. Okay? Right. Then we have proved that all the distinct elements of H are given by the identity B1 up to the power of uh, B to the power of M minus 1. So all these elements are distinct and those are the only elements in H. Right? Now, how have we proved this? If we have all these elements to be, some of them to be the same, if not every one of those elements are distinct, that means we have at least two to be the same element, right? Then for some A1, A2, where A1 and A2 lie between 0 and M, and without loss of generality, I will suppose A1 is less than A2, right? We have B to the power of A1 is equal B to the power of A2. What do we do next? We take the inverse of this element on both sides and we see that B to the power of A2 minus A1 gives you the identity, right? Now, this is a contradiction. Why? Contradiction to the definition of of the order of an element. Because we have already taken M to be the smallest positive power of B, giving the identity. And we know that A2, A1, they are both less than M. So the difference is also less than M. Because A2 is greater than A1, this is a positive number. And now we have another positive power of B giving us the identity where this number is actually less than M. So this is a contradiction. Therefore, the supposition must be wrong. That means we must have all these elements to be distinct. B to the power of 0, B1 up to Bm minus 1, they all must be different from each other. Right, so this is where we are at now. We had to go from here. Right, now in the next step, we have to show that these are the only elements in H, right? All these powers of B are the only elements in H. Now so far we know that all these elements are distinct, but could we have more elements, right? Powers of B that are in here, that are not in here. So in our next step, we will show that these are the only elements that could belong in this set. Right. How do we do this? We will use a little bit of number theory in here. Okay. Right. Let's take if bt is any power of b. With division algorithm, using division algorithm, we can write division algorithm for t and m. We can write t equals mq plus r, where q is the quotient when we divide t by m, and r is the remainder which lies between 0 and m. Now we want to see if we have any other positive power of b outside of that given set. So far we have these elements b0, b1. Now we want to see whether for some t that is greater than m, we have that element to be in this set, right? So then we have b to the power of t written as b to the power of mq plus r, which simplifies to, because the order of b is m, we have b to the power of m to be the identity. So we have identity raised to the power of q. This simply is br. And what does this tell you? R is any element between 0 and m. So this is actually an element since R is either equal to 0 or less than m. We have BR to be an element in the set. M minus 1. Right? So no matter which t that you pick, we see that using division algorithm, all these elements actually belong to this set. For some t, it will always be some element in this set. So we understand all the elements that are in this group are these, and they are different from each other. Right. Now, what is the next step? We have to show that m is equal to n over d, where d is the greatest common divisor of d is the greatest common divisor of n and s. Okay. Now we know b is taken to be a to the power of s, right? And this implies, this is actually if and only if, b raised to the power of m, we take the power of m on both sides, right? Because b raised to the power of m is the identity, this element becomes the identity. What does this tell you? This tells you n divides sm, or I'll write ms. Why is that? Why do we have n to divide ms? Because if we go back, we know the order of A is n, the number of elements in G. Order of A is n. Okay? This is because order of A is n. Right. Now, from the definition of the order, right? We know that if the order of A is given to be n, that is the smallest positive integer That is, I will write this part because I don't think we went over this discussion where once you get to this point, you can conclude n divides ms. We surely know ms must be this number, ms, m times s, must be greater than or equal to n. But why do we have this divisibility? Now, to see why n divides ms, we understand by definition, ms must be greater than or equal to n, right? Why is that? Order of a is n. So n is the least positive integer such that a to the power of n gives you the identity. Now we have for some other integer sm, both of which are positive integers, right? We have the power of a to be the identity. Okay, the power of a to be the identity. So this tells you ms is either n or a value greater than that, definitely not less than n. Once again, using the now, in order to see why n divides ms, we will use the division algorithm on ms and n. Now, ms is a number that is greater than or equal to n. So by division algorithm, using the division algorithm, there exist integers q and r such that ms is equal to q times n plus r, where q is the quotient which we get, the integral integer value which we get when we divide ms by n, and r is the remainder which lies between 0 and n, right? Now, let's go back. A raised to the power of sm is simply a raised to the power of qn plus r, which you can write as a to the power of n times q times a to the power of r. Now this is the identity, therefore this ends up being ar, but because we know that a to the power of sm is the identity, now we have ar to be the identity, right? Ar to be the identity. A to the power of r to be the identity. Okay, and r is a number which lies, r is a positive number, a non-negative number which is less than n. What is the only possibility that lies over here for r? It has to be 0. Why is that? We already know the order of a is n. In other words, that means the least positive number for which the power of a is the identity, and n is the smallest number by definition. That would give you the identity once you raise a to the power of n. But now we have a raised to the power of r, which is a number that is smaller than n, giving you the identity. And it lies between, it could be equal to 0. It lies between 0 and n. So our only option at this point is for r to be 0. It can't be any other number because if you take r to be a non-zero number less than a positive number less than n, it would violate the definition of the order of an element. So we must have r to equal 0. So going back over here, we have ms to equal q times n plus 0, which we will omit writing. What does this tell you? This tells you n actually divides ms, right? N actually divides ms. Okay. Right. Now, we need to show that. Now we know, after all this, we know that H has m number of elements. Those are the only elements, and the elements are given by b to the power of 0, which is the identity b1 up to bm minus 1, which are all distinct. So it has exactly m number of elements. Now our next step is to show that m is equal to n over d. uh, over D. Right. So D is the greatest common divisor of N and S. D is the GCD of N and S. Then, by definition of the greatest common divisor and its properties, we can find two integers. Let's take it to be U and V. Then there exists integers U and V such that D is equal, such that we are able to write D as a linear combination of N and S. D is equal to UN plus VS, right? Once you have the greatest common divisor of N and S, we have actually, there is a way to get this linear combination even using the Euclidean algorithm, right? You can write the greatest common divisor as a linear combination of the two numbers N and S. So we can find unique integers U and V giving this linear combination. Right. Now, D is the greatest common divisor of N and S. So by definition, D will divide N, D will divide S. So what I'm going to do is I will divide each term over here by D. Right? Since D divides both N and S, we have 1 equals U times N over D, which is an integer, plus V times S over D. Once again, you have an integer over here, right? This is in the set of integers, Y, because D divides both N and S. Now, what does this equation tell you? This tells you these two values, N over D and S over D, must be relatively prime. Must be relatively prime. I think we have, so from this equation we get we conclude that N over D and S over D are relatively prime. Right. Now, we want to show in our next step, we want to show that no, we want to find the smallest positive M such that N divides MS, right? N divides MS. Okay. So from here, we know that N actually divides MS, right? Now we want to find M and we want to conclude that M equals N over D. Now we want to find the smallest positive M, the smallest possibility that M could take, so that N actually divides MS. What is the smallest number M could take where N divides MS, right? Now to do that, we need this equation where we have concluded that N over D and S over D are relatively prime. Now, what does this give us? From this, observe that now M over S is divisible by N. So let me write M over S divide by N. What do? I will rearrange the terms to get this. This is equal to N over D, where each S and N I will divide by D. Now, we know that Yeah, this is n over d, n over d. These two are relatively prime, right? These two are relatively prime. Sorry. If we go back, let me see. Yes, we will use this result, which I have given in our last lesson, in the previous lesson. If R and S are relatively prime, and if R divides Sm, then we must have R to divide M, right? Now coming back over here, ms is divisible by n, right? So we can use, because this is an integer, we write it to get, and we rearrange the terms to get, and we not just rearrange, we actually manipulate the terms to get the terms s over d and n over d. Now, what you get over here is an integer because ms is divisible by n. Not only that, these two integers are relatively prime. So our only possibility is that by that result that we just referred to, n over d dividing m, right? So we can write since the greatest common divisor of n over d and s over d is equal to 1, that means those two are relatively prime. We have n over d to divide m. Therefore, we must have the smallest possible m to be equal to n over d. That ends our proof. Okay. Right. Now, using this result, we will look at some examples. Let's consider the group. Let's consider Z8. This is under addition modulo 8. Right? And we know that this is generated by 1 as well as its inverse for sure, right? Now, observe that the greatest common divisor between, let's say, 3 and 8. GCD of, let's take 3 and 8. This is equal to what? Greatest common divisor between 3 and 8. 3 is a prime number. It does not divide 8. Therefore, those two are relatively prime. So the greatest common divisor is 1. Right? So what does this tell you? By the theorem, by the previous theorem, we know that 3 generates a subgroup of order n over d. In this case is 8 over d, the greatest common divisor, which is 1. 8. Right? A subgroup of order 8. In other words, a subgroup containing 8 elements. It must be Z8, right? Because this group contains 8 elements and 3 generates a subgroup of it containing 8 elements. So it has to be generating the group itself. So we understand 3 generates this group. right? Is it clear to you? I'm simply referring to, yeah, this theorem. If we go over the statement once again, G is a cyclic group. So we have taken an example of a cyclic group, Z8, right? With n elements. So in Z8, we have 8 elements. It's generated, we can pick any generator. So we are going with the easiest one, which is 1. 1 generates Z8. And the number of elements in it, 8. Let B be any element in G. So what are we doing? We are taking any element in G. We have picked, we actually have picked 3. Why is that? If you look at this group, right? What are the elements in this? We've got 0, 1, 2, 3, 4, 7. Not only that, 1 raised to the power of 0 gives you 0. 1 raised to the power of 1 gives you 1. 1 raised to the power of 2 gives you 2, right? So the element, the number here itself gives you the element. Okay, 1 raised to the power of 3 gives you 3 likewise. So what, with respect to this theorem, we take any element, right? And we find the corresponding power. Now, in this case, right? In this case, we actually have considered the element 3. And it is the power of 1 raised to 3. 1 raised to the power of 3, right? So how do we find the subgroup that it generates? First, we have to find the number of elements, right? Once again, referring to the theorem, we see that B generates a cyclic subgroup H of G containing N over D elements, where D is the greatest common divisor of N and S. So what do? We first of all find the greatest common divisor of 3 and 8, which is 1. So these two are, because these two are relatively prime, it's 1, right? And we take n over d. N in this case is simply 8. It does not change. D for these two numbers, 1. N over d is 8. So 3 generates a subgroup of Z8 containing 8 elements. In other words, all the elements. So it has to be a generator for this. Okay. If we take 4, the element 4 from Z8, right? This is equal to 1 raised to the power of 4. So let's first of all find the subgroup generated by 4. Let's calculate the greatest common divisor of 4 and 8. What is the greatest common divisor between the two? That is 4, right? The greatest common divisor is 4. Right. So 4 generates a subgroup of order n, which is 8, over d. D is 4. This is 2, right? So 4 generates a subgroup of order 2. That means this subgroup can have only 2 elements. It definitely has 4 raised to the power of 0, which is the identity, and then 4. These are the only 2 elements. You don't even have to check for the other elements. If you want, 4 raised to the power of 2 would be 4 plus 4. Divide by 8, take the remainder. 4 plus 4 is 8. Divide by 8, the remainder is 0. You are back at this element. 4 cube will give you 4. 4, you take the fourth power once again at 0. So this is the group, right? And then let's take 6. The element 6. And 6 is equal to what? 1 raised to the power of 6. Let's find the greatest common divisor of 6 and 8. What is the greatest common divisor of 6 and 8? That is 2, right? 2. So we have 6 to generate a subgroup of order 8 over 2, n over d, right? So of order 4, that means it has 4 elements. So let's start writing writing the elements in this group. We start off with the identity, which will simply relate to the 6 to the power of 0. 6 to the power of 1 is 6, right? Then we have 6 to the power of 2 would be 12 divided by 8, take the remainder, which is 4. And then 6 to the power of 3, you have 18 divided by 8, take the remainder 2. So we have 0, 2, 4, and 6. These are the only elements. We have 4 elements. All right. And then, so these are the groups. Is it clear? Is it clear? Do you all have any questions? Right. Okay, with this, we'll go to corollary. Okay. If A is a generator, A is a generator. Wait. Okay, if A is a generator of a finite cyclic group G of order n, then the other generators of G are the elements of the form AR, where R is relatively prime to n, right? If A is a generator of a finite cyclic group G of order n, then the other generators of G are the elements of the form A to the power of R, where R is relatively prime to n. Why do we have this? If we go back to the previous theorem, right, and refer to the second statement, right? This tells you these two subgroups are the same. Now, A is the generator of G, right? These two subgroups are the same if and only if the greatest common divisor, the greatest common divisor of N and S is the same as the greatest common divisor of N and T, right? So this is exactly what's being referred to over here, right? If A is a generator of a finite cyclic group G, now G is generated by A of order n, then the other generators of G are the elements of the form AR, where R is relatively prime to n, right? Where R is relatively prime to n. So it comes directly from this as an exercise. Please try and using this theorem, prove that corollary, right? I'll give that as an exercise. Right, but we will be using it to find generators of cyclic groups. Okay. Once again, we'll look into this example with Z8. This has elements 0, 1, 2, up to 7, right? We know one generator of this, which is 1, right? Okay. Once again, 1 raised to the power of 0 is 0. This is 1. This is 2. This is 3, likewise. So all these elements are given, right? Now, what is the order of this group? 8. How do we find the other generators of Z8? How do we find the other generators of Z8? By finding numbers, right? All these powers, right? Which are simply these elements. We will find the elements that are relatively prime to 8. What are the elements we have to be relatively prime to 8? We've got, so first let me write, we wish to find R in this set. We've got 1, 2, 3, up to 7, right? R in this set, which are relatively prime to, which are relatively prime to 8. Right. So what are the elements that are relatively prime to 8? What are the elements? Do we have 2 to be relatively prime to 8? No, the greatest common divisor between 2 and 8 is simply 2, right? 3?
Yes.
Yeah, and then what else? 4? No. Then we've
5.
got 5. Then 6?
7.
No. Finally, we have 7. So we've got, we have R to be 3, 5, 7, right? 1 we can disregard because we know this group is generated by 1. Okay, we have to look at the rest of the elements. 3, 5, 7. So we understand because the GCD of R and 8 is equal to 1. For R equals 3, 5, 7. From the previous corollary, we have Z8 to be generated by 1, we already know, 3, 5, and 7, right? 3, 5, and 7. Okay, so we've got 8 elements all together. We know 0 will simply generate the trivial subgroup which contains the identity element, only the identity element. We know what the identity will generate, the trivial subgroup. Now we know what 1, 3, 5, 7 all generate. They will all generate the same group, the group itself, Z8. Now we have a few more elements left in the group, which will be 2, 4, and 6, right? So let's start off with element 2. We want to see the subgroup diagram for Z8, right? So, okay. Let 2 be an element in Z8, right? Now, what is the order of the subgroup that is generated by 2? I did it also. Order of the subgroup generated by 2. How do we find the order of the subgroup? You can definitely list down the elements and get it, but I think we did it just now, the example also. Did we not? No, not that one particularly, but we have done something very similar. What is the order of the subgroup generated by 2? How do we find it? Using that previous theorem, right? You take 2 from Z8. We know we can write 2 as 1 raised to the power of 2. Then what do? We find the greatest common divisor of 2 and 8. So if we compare all this information with the elements or the details that were given in the theorem, this will simply be our B, 1 will be A, 2 will be S, and N will be the order of this group, right? So we find the greatest common divisor of 2 and 8, which ends up being 2. Therefore, the order of the subgroup generated by 2 is given by n over d. N is 8. The greatest common divisor between these two is 2. This is equal to what? 4. So we understand this subgroup will contain 4 elements. Is it clear to you? So we can write starting at the identity 0. This is 2 to the power of 0. 2 to the power of 1 is 2. 2 to the power of 2 is 4. 2 to the power of 3 is 6. 2 to the power of 4 is 8, which gives you the element 0 because we take addition modulo 8. Right? So these are the only elements in this group. Is it clear?
Yes, madam.
Right. Okay. Now observe. Now we are left with 2 more elements, 4 and 6, right? 4 and 6. Now, okay. Once again, if we refer to the corollary, right? I want to show you all something. Right. If we go back and refer to the corollary, right? If A is a generator of a finite cyclic group G of order n, then the other generators of G are the elements of the form AR, where R is relatively prime to N, right? If we go back to that corollary and if we simply, now this is it's a cyclic subgroup of Z8. So it's a cyclic group on its own, right? So this group I will see, and it's the generator for this group is simply 2 under the binary operation addition modulo 8. Right? So this element will be written in this form, right? If I write all these elements as the powers of the generator, which is 2. We have 2 raised to the power of 1, 2 raised to the power of 2, 2 raised to the power of 3. Okay. What other generators are there for this group? What are the other generators? Is it the only one, or do we have any other generators for the same group? Once again, going back to the corollary, now we are simply taking G to be this subgroup, right? Let me take this paper without having to. Okay, right. Now, if you compare the two, right? You compare the two. Now, G is this group, right? Binary operation is addition modulo 8. A is simply 2. So we want to find the other generators of this group, right? If A is let's read the statement once again. If A is a generator of a finite cyclic group G of order n, so the order of this group is 4 now. The other generators of G are the elements of the form AR. Now we have written all the elements in this group in that given form, generate the some power of the generator. where R is relatively prime to N. So to find the other generators, what do we have to look at? All these powers, right? And we have to find the numbers which are relatively prime to N, right? In this case, 4. So what are the numbers that are relatively prime to N? N meaning the order of this group now, which is 4. What are the numbers? How do we find the other? Go ahead, Pina. Do we have any other generator for this group? We know that 3 is relatively prime to 4, right? 3 is relatively prime to 4. We will disregard 1. Why is that? 2 raised to the power of 1 is simply 2. And 2 is the generator anyway, right? If we go to this element, we simply have to look at the power over here, 2. 2 and 4, GCD of 2 and 4 is simply 2, the greatest common divisor. So this will not be a generator for this group. However, G, because we want them to be relatively prime. In other words, the greatest common divisor to simply be 1. This index 3 and 4. What is the greatest common divisor of 3 and 4? It's simply 1. So 3 and 4 relatively prime. The corollary tells you the generator raised to this power must be, the element, the generator, yes. So 2 in this case, raised to the power of 3 must be a generator for this group, right? Therefore, 2 raised to the power of 3, which is equal to 6, is also a generator uh, for this same group. And we have actually seen this in this previous example, the example that we did right before the corollary here. We found this subgroup. It contained elements 0, 2, 4, 6, which is exactly what you see over here, right? So now we see these two subgroups, the same subgroup, right? Generated by 2 and 6. And this is a subgroup of Z8. Is it clear to you? What are we actually doing? Using the corollary and the theorem, we are looking at all possible generators and every other subgroup that are generated by the other elements of the group, right? And we are trying to get the subgroup diagram. Do you all have any questions? Is it clear up to this point?
Clear, madam.
Right. Now we have almost all the elements 1, 3, 5, 7, 2, 6. Only 4 is not there. Right. So what is the order of, I think we have, I will simply refer to it. Yeah, we have gotten the subgroup generated by 4 over here for the same group Z8, right, which consists of 0 and 4. So I will simply refer to it. 4 we have seen from the previous example to be 0 and 4. And these are the only subgroups. And then the subgroup diagram. We start with the group, right, which is generated by 1, 3, 5, 7. These are the proper, these are the two proper subgroups. So we have the subgroup generated by 2, which is the same as 6. And right below it, and this is a subset of this set. These two are groups under the same binary operation. Therefore, this is a subgroup of this, right? And we have the subgroup generated by the identity. Do you all have any questions? Can't see. Do you have any questions? No. Right. Okay. Now, the next topic, generating sets. And Kaylee, digraphs, sometimes we call it diagrams. I'll go with diagram. Okay. Okay, so now, so far we have seen groups that are being generated by just one element. But it doesn't have to be one element. We could have more than one element generating the same group, right? So that's what we are going to talk about uh, in this section, right? Let's take G to be in the usual notation to be a group, right? And A be an element in G, right? Some terminology that we have to know first before we get to generating sets, right? Once again, what sort of a subgroup is this? It's a subgroup generated by A. So it's the smallest subgroup of G containing A, right? By definition. This is the subgroup generated by A. It's the smallest subgroup of G containing A. So let me write the smallest subgroup of G containing A. Right. Right. Now, what exactly are we planning on doing in this section? Sometimes I could ask, I can give you two elements, maybe let's say A and B, right? In the group, let's take A and B, and I will ask you to find the smallest subgroup of G containing both these elements, right? So intuitively, that would be the smallest subgroup. So if you compare it with this definition, it should be the smallest subgroup of G containing the smallest subgroup of G containing the two elements should be the subgroup generated by those two elements, right? So what exactly do we want in this case? We want to find the smallest subgroup H containing, let's say, two elements A and B, both A and B in G, right? What sort of elements can we expect for H to contain? If A and B are both in H, then we must have all powers of A, all powers of B to be in H because H is a subgroup of G. So it's a group on its own. Not only that, we should have any product of A and B in H. You take any power of A, any power of B, and you take the product of those two. It must also belong in H, right? So if A and B are uh, both in H, we must have A, let's say N and BM to be elements in H for all NM in Z, right? Then we say that A and B are generators of H, right? As in this case, we say that A is a generator, sorry, if G is, say, generated by simple G, we say that G is a generator for G. And if H is the subgroup, it's the smallest subgroup containing both A and B, we say that A and B are generators of H, right? Okay, let's take a look at one example that we are very much familiar with. Let's go with, yeah, let's go with the cyclic group easy, an easy example, right? We have 0, 1, 2, and 5. This is generated by definitely 1, then we have another generator, 5, right? We have another generator, 5. Okay. Uh, what other generators do we have for Z6? What are the other generators of Z6?
2 and 3.
2 and 3, yes. I'm asking, can we, it's actually very good, by the way. It is generated by 2 and 3. But my question was to find another single generator for Z6. Do we have another generator for Z6, just one element?
No, madam.
No. Why is that? Why is that? Once again, we are going back to that corollary, right? If I simply turn it over, A is a generator of a finite cyclic group G. Let's take 1 to be the generator of Z6, right? It has two generators, 1 and 5, uh, which, yeah, let's just go with 1, right? And Z6 is of order 6, right? If there is another generator, it can only be of the form AR, where R is relatively prime to N. So what are the numbers between 0 and 5 that are relatively prime to 6? We only have 5. We only have 5, right? Because in this group, we have all the elements 1 raised to the power of 0, 1 raised to the power of 1, 1 to the power of 2, to the power of 3, to the power of 4, to the power of 5. That's it, right? So all these powers, 0, 1, 2, 3, 4, 5. Out of those, the only numbers that are relatively prime to the order of the group, which is 6, would be 5, right? Is 5, because 1 is already a generator. You don't have to consider that one apart from that, right? That's why we have these two to be the only generators, single element generators, right? Now, going back to generating sets, right? More than one element. Why did you say that you have generators 2 and 3? How would you justify that answer? Okay, let's go over that. Let's take H to be a subgroup of Z6 that is generated by which is generated by uh, 2 and 3, right? So this set is a generating set for H, right? So this is a generating set for H. Now, observe that if this is a generating set for H, any power of 2, any power of 3 must belong in H. Not only that, when you add these two, when you apply the binary operation to these two elements, they also must belong in H. Now see, note that 2 addition modulo 6, 3 is equal to what? 5. 5 is an element in H. 5 is an element in H and 5 is a generator for Z6. Therefore, we can conclude we must have H to be equal to Z6. Why is that? Just because 5 is in there, how can we conclude that H must equal Z6? Why is that?
We have only two generators.
No, now we have shown that 5 is an element in H, right? As soon as we see this, 5 is an element in H and we know that 5 is a generator for Z6. So the only option for us in the case of H is to have it to be Z6. Why is that? If 5 is in H, right? Now, and we have shown that 5 is in H, every power of 5 must also be in H. And every power of 5 means all these elements, right? Because it generates this set. So all elements that this element generates must belong in H. That means all these elements must be in there. In other words, because we have taken H to be a subgroup of Z6, right? It must equal Z6. That's all. Okay. Is it clear? So in other words, Z6 is actually generated by 2 and 3. So for the same group with just one generator, we have gotten another generating set. Z6 is generated by the two elements 2 and 3 as well. So we can write generated by 2 and 3 as well. Okay. Is it clear?
Yes, madam.
Okay. Now the next theorem. Okay. Let's take, sorry, Hi to be a subgroup of a group G for each I in any index set capital I, right? Then, now here G is a group, okay? G is a group, Hi is a subgroup of G for each I. Then we must have the intersection of all these subgroups to be a subgroup of G as well. Intersection of all these subgroups must also be a subgroup of G, right? We have to prove this. Right, now to prove that this is a subgroup of the group G, we will use the subgroup criterion. First of all, we have to show that the intersection itself is not empty. How do we do that? Why is it not empty? Why is it not empty?
Identity is there.
Yes, very good. The identity is there. How do you say that the identity is in there?
Identity is an element in the capital I group.
Capital I group. There is
No.
now this capital I is any index set. It's an index set, like the set of natural numbers, integers, real number. It's an index set. All these indices come from this index set. It's not a group or anything uh, related to these two groups. It's simply an index set. But why do we have the identity to be in this intersection?
Because HI is a subgroup of G.
Yes, Hi is a subgroup of G and
Therefore, HI, the identity is an element in HI.
yes, very good. For each I, Hi is a subgroup. And these are subgroups, so the identity is in there. Identity is in each Hi. Therefore, it must belong in the intersection because the intersection contains all common elements, right, for each Hi. So we can write the intersection of Hi is not empty since the identity E is in Hi for all I in this index set. Each Hi is a subgroup, so it's a group of its own. Identity is in there. Therefore, the intersection also contains the identity. So the identity is in the intersection. It's not empty, right? Now to use the subgroup criterion, we are taking any two elements from the intersection. Let's take A, B, two elements from this intersection, right? Now what? We have to show that AB inverse is in this intersection. How do we do that? We need to show that AB inverse is in the intersection. How do we do that? Each Hi is a subgroup of G, right? So they are groups on their own. Therefore, when you take two elements AB from the intersection, this AB is in Hi for each I, right? In each Hi, you have the two elements AB. Because Hi is a group on its own, AB inverse must belong in there. Why? It's a group closed under the binary operation, closed under inverses. Therefore, AB inverse is in each Hi. Once again, since every Hi contains that element, it must belong in the intersection, right? Now, after this, we can write we have AB to belong in Hi for all I in the index set I. Since Hi is closed under the binary operation, and is closed under inverses, we have AB inverse to be in Hi for all I in I. Right? Now each Hi contains this element. Then we must have this element to be in the intersection. Right? We must have AB inverse to be in the intersection. Therefore, by the subgroup criterion, this intersection is actually a subgroup of G. Okay, right. Do you all have questions up to this point? Any question? No questions. Right. Okay, then let's get on with the other definition. Let's take G to be a group. Let G be a group. Now we are actually defining generating sets. Okay, let G be a group. And let's take AI to be an element in G for I coming from some index set I. The smallest subgroup of G containing these elements, these AIs, right, is the subgroup generated by these elements AI. We are simply extending the definition of a generating set with one element, right? So over here we have maybe more than one, more than one element, a generating set, right? One or more elements. Subgroup generated by AI. Now, if this gives you the full group, all of G, then we say that this is a generating set for G, right? And if it is a finite set that is generating G, we say that G is finitely generated. Now, in all the examples that we've done so far, the group was actually finitely generated. We saw the group being generated by one element, and in one instance, just two elements, right? The same group by just two elements. So in any case, those were finitely generated. Okay. Right. With this definition, let's go to the next theorem. We have, let's take G to be a group. G is a group and AI is in G for I coming from some index set. Then the subgroup H of G generated by this generating set, all these AIs, has as elements precisely the elements of G that are actually the finite products of integral powers, has as elements those elements Finite products of integrals, or in other words, integer powers, right? Integral powers of AI, where all these, where powers of a AI may occur several times in the product. In the product. Okay. Let's do the proof. Okay, now let's go over the statement once again. G is a group, AI is in G, for I coming from some index set capital I. Then the subgroup H of G generated, now we are taking H to be the subgroup generated by all these elements AI, right? And what sort of elements does it have? It has elements of G, right, that are finite products of integer powers of AI, where powers of a fixed AI may occur several times in the product. So, for example, let's take, now I'll just, before writing the proof, if we take the generating set to be A1, A2, maybe these two elements. What sort of elements do we have in H? It has finite products of integral powers of or integer powers of A1 and A2. So we have maybe A1 8 is in there, A1 8, A2 7, and A1, let's say, -2. This is also a possible element in H, right? Uh, so these are the types of elements that you can get in H. That's what it says in the theorem statement. Okay, how do we prove that? This is true. Now what are we going to do is we are going to take K to be the set of all finite products of integer powers of AI. So let me write, let K denote the set of all finite products of integral powers of the AI, right? Now, H is generated by A1, H is generated by all these AIs, and K is a set containing all finite products of integer powers of these AIs. Then we must have K to be a subset of H. We must have K to be a subset of H, right? Why is that? H will contain all powers of these AIs and their respective products, right? And K contains some of these products. What sort of products does it contain? Products of integer powers, finite products of integral powers of these AIs. So K contains, seems like K contains some of these elements, not all, but some of these elements in H. That's what it seems like, right? But we want to show at the end, K is actually equal to H. How do we do that? We will show that K is a subgroup of H. And that would be the proof. Why would it conclude that K must equal H once we show that K is a subgroup of H? Why? Because all these AIs generate H. In other words, by definition, H is the smallest subgroup containing all these AIs, right? Now, here, K denote the set of all finite products of integral powers of AIs. In other words, K also contains all these AIs, right? All these AIs must belong in K by definition of K. And it's a subset of H. If we show that K is a subgroup of H, the only possibility would be for K to equal HY. Now, in that case, K is a group containing all elements AI, and H is the smallest group containing all elements AI, right? And because K is a subset of H, K is not containing H, it's contained in H. Therefore, the only option for us at that point would be for K to equal H, right? So that is exactly what we are going to prove. We will show that K is a subgroup of H. So let me write it. Okay, we will show that K is a subgroup of H so that we can conclude K equals H since H is the smallest subgroup, containing the AI. And K is a subgroup containing these AIs. In that case, K must equal H, right? Now, but this is something that we have to prove. Okay, so now observe that K is not empty. Not only that, we actually will prove, we will show that K is closed under the group operation, binary operation. It contains the identity. Not only that, it contains all inverses, right? Uh, if it satisfies all these properties, we can simply say K must be a subgroup of H. Now observe that the identity, right. Now, first let me write a product which would refer to applying the binary operation, right? To any two elements in K. Let me write a product of elements in K is again in K. It's very clear. Why? You take finite products of integral powers. Then you take the product, you end up with finite, another finite products of integral powers. Okay, right. Elements in K is again in K. Then to show that the identity is in there, since for any I you take its zeroth power, you get the identity, right? In K. So we have the identity E in K. Now to show that it's closed under inverses. To show that it's closed under inverses. Right. Let's take any element K in the set capital. Okay, for every simple K we take from this set, right? Take, let's consider the product that gives us K. So finite products of integral powers of AI. Take the product. Now this actually will show you how to form the inverse. Take the product giving K Then with this product, we form or we build, we construct another product, right? Then form a new product with the order of AI reversed and giving opposite sign on all these exponents, all the powers, and giving opposite all exponents. All exponents. What we have is K inverse. Which is also in K. Why is that? Why do we have that to be in K? Because that would once again be a finite product of integral powers of AI. We are simply reversing where all these AIs are. We will simply reverse the AIs, take all the exponents and multiply it by a -1. So once again, we see an element in K, right? Now, as an example, let's take K to be of this form. A1 -2, A3 4, and let's say A8 2. Then K, how do we get K inverse? Reverse all these elements, starting from this last one. Write it over here, A8, and this exponent, multiply it by a -2. Then we come to the next element, put it over here, A3, multiply by a -4. Come to this one, A1, multiply by a negative, you have 2. It's easy to see that this is the inverse of K and K is the inverse of K inverse by taking K inverse. We have A1 -2, A3 4, A1 squared. These two will give you the identity, right? Then we have A1 -2, A3 4, the identity, A3 -4, A1 squared. Once again, these two, identity times this element gives you the element itself. These two together will give you the identity. At the end, you see, once you are down to these two elements, A1 to the power of -2 times A1 to the power of 2 gives you the identity. Okay, is it clear? Therefore, we see that K is a subgroup of H because it satisfies all conditions of being a group. It's a subgroup of H, and we are done. Okay, now we are down to Cayley diagram. Sometimes we call this a diagram. Or the Cayley digraph. Why do we call it the digraph? Because it's a directed graph. We are actually constructing a directed graph. That's why it's called a digraph, but we will refer to it as Cayley diagram. Right. Now, this gives you a representation of a group in the form of a graph, right? Uh, say you have G to be a group and a generating set S. If we go back to Z6, the last example we did, we saw the generating set to be, first of all, we can generate the entire set by just a single element 1. And on the other hand, we saw another generating set containing the elements 2 and 3, right? So we start off with the group, find its generating set. It could either have one element or more than one element. Doesn't really matter, right? How do we get the corresponding Cayley diagram? First, every element in the graph will be denoted by a vertex in the diagram, right? By a vertex. All of us, now let me go back to graphs a little bit. How do we represent a graph? A graph is actually given by a pair V and E in the usual notation. By V, we represent vertices. By E, we represent edges. Vertices are these nodes, right? And edges correspond to a pair of vertices, pair of nodes. If you have a line connecting one vertex to another, that is what we call an edge. So a line cannot exist as a small segment. It has to be connecting two vertices. In that case, we say that, for example, a little bit of graph theory. If by G we denote a graph, say you have three vertices A, B, C, right? So G can be given by the pair VE, where V is the vertex set. So it has three vertices A, B, C, and E is the edge set. This is one edge connecting AB. So AB will give you one edge, the other edge will be AC, right? So this is the sort of representation that we are going to build for our graph. For our group. Okay, so let me first uh, list down. Let me first write. It's a representation of groups. Um, Let G be a finite group. And S be a generating set. Let S be the generating set for G, right? Okay. So then we can find a directed graph. There is a directed graph. Let me write, there is a directed graph. There is a directed graph representing the group in terms of the generators or the elements in S, right? In S. How do we build this diagram, or how do we get this representation? First, let me write the diagram. First thing is vertices will be elements of G, right? Now, what is a directed graph? If we go back to this example of a graph, this here says there is a directed graph representing the group in terms of the generators in S. What do we mean by a directed graph? A graph in which all edges are given a direction. So if I put arrowheads like this, in this case, the graph G has vertices A, B, C. It only has edges A, B and C, A. There is no edge AC, right? There is no edge AC. We only have C, A, right? Because now, in the earlier case where we didn't have a direction, instead of writing AB, we could have written BA because those two would represent the same edge. Once you give a direction, you have to have this initial vertex. Now, in this case, the arrowhead is from A to B. Initial vertex is A. This terminal vertex or the ending vertex is B. So AB is the edge. There is no edge BA. This is a directed graph. Right. Back to the Cayley diagram of a graph. How do we build it? First, vertices will be elements of G. Elements in G. Right? Elements of G. And then each generator in S will be denoted by one type of an edge. One type of an edge. For example, what does this mean? If we have S to be this generating set, for some group G, we have, suppose the generating set S to be containing the elements A2. We will look at concrete examples, okay? In this case, I will represent this generator. This generator will correspond to this edge. Let's put it that way because these are also elements in G, right? So they will have their own, they will be denoted by a vertex. So the correspondence or the action all these elements have on other vertices, other elements in G is given by this edge, right? So this edge, and I will denote B by this dashed edge, right? This solid edge will, directed edge will correspond to A. This will correspond to, now we have two types of edges, okay? What does this give you? Now, if you have two vertices in the graph, X and Y, and this solid edge, let's suppose this is X, Y. What does it mean? This means X times A is equal to Y. X times A is equal to Y. So we have multiplication on the right. Let me write over here multiplication. When I say multiplication, we are actually referring to the group operation, right? We simply write it as multiplication on the right. Multiplication on the right. Right? Now, this is when we go in the given direction from X to Y through this H corresponding to A, we have XA equals Y. If we go in this direction from Y to X, but the direction is given from X to Y. If you go in the reverse direction, in the opposite direction, we are actually talking about, or we are considering A inverse. If A is in this direction, A inverse must be in the other direction. A inverse must correspond to the other direction, right? Right. So let me write it as in the opposite direction. For this same segment we are talking about, in the opposite direction. In the opposite direction, we start at Y. On the right, we take inverse, A inverse is equal to X, which has to be true, right? We have XA equals Y. We take A inverse on both sides on the right. This will simply be, if I write it, XA equals Y, take A inverse on the right. We have XA inverse equals YA inverse. This means X is equal to YA inverse. Exactly what we see over here, right? Okay. Right. Now, what happens if a generator is its own inverse? Right now, in this case, A in this direction gives you A, the other direction, A inverse. This direction for B, the other direction, B inverse. What if the inverse is the element itself? Right? Okay, let me write when a generator in S is its own inverse. We simply denote it by omitting the arrowhead. We simply disregard the arrowhead if the inverse of the generator is itself, right? From the edge. Okay, so for example, in here we have this other generator B, right? Say the inverse of B is itself, right? So for example, if for this particular generator, B squared is the identity, this means B is its inverse, right? So in that case, we will denote B by simply this dash line, no arrowhead, okay? That's what it means. Let's take a look at few examples here. Let's take Z5, which is generated by 1, right? So now in the generating set, we have only one element, right? 2, 3, 4. These are the elements. What is our generating set? Generating set S contains only one element. First thing is we will denote this one. We will denote 1 by a type of an edge. We will simply go with this solid edge, right? This directed edge. Why do we have this arrowhead? Because the inverse of 1 is 4 for this particular group, right? Now, so we have to have the arrowhead. First, we start off with 0. We have 0, right? If I take this edge from 0, right? What is the other element that should pop here? We have 0 times 1, which simply means, now, if you go back to this one, the definition tells you between two vertices when you have this edge, this means x times a. This multiplication simply refers to the binary operation defined on the group, right? Must equal what? The other, the value of the other element in the group that gives you this value, right? So now we have 0. What is the binary operation? Addition modulo 5. Addition modulo 5. This refers to 1. So we are only adding 1 on the right. This gives you what? 2. 0 plus 1 is, sorry, 1. 1. Okay. This gives you 1. 0 plus 1 is 1. Divide by 5, take the remainder, you have 1, right? Okay. So over here, we have 1, right? Now, from 1, this corresponds to this one. Now we are starting at 1. To 1, we add this edge is for the generator 1. We add 1. 1 plus 1 divide by 5, take the remainder, you have 2. So this other element is 2. So from 2, we have 2 now. 5, 1. We are only adding 1 because there is only one edge. To this edge corresponds the value 1. 2 plus 1 divide by 5, take the remainder. You've got 3. This is 3. So 3 to add 1 to 3, you get 4. Add 1 to 4, you get 5. Divide by 5, take the remainder, you have 0. So this will be the Cayley diagram for Z5 with the generating set 1. With the generating set 1. Right? Okay. Now observe that for each vertex denotes an element. Sorry. Denotes an element in the group, right? Denotes an element in the group. This is a connected graph. What you see is a directed connected graph, okay? A connected graph, not only that, at each element, there is an arrowhead, there is a edge where the arrowhead moves away from it, and there is an edge where the arrowhead is pointed towards it, right? At each vertex, this is true. Now let's take a look at another example. Let's go with Z6. This is also, first of all, let's take this generating set 1. So it has these elements. Generating set S is simply 1. Therefore, for 1, I will consider this solid edge, directed edge, because the inverse of 1 for this particular group is 5. Right? Start at 0. If I go in this direction, there is no, it doesn't have to be this, in this as a polygon, right? You can take any representation. However, these arrowheads, the relation must retain. It doesn't have to be as a polygon. We have 1, 2, 3, 4. Then we have, say, 5. And then we have 6. Here, this is a different representation. It doesn't have to be like a polygon, right? This is for Z6. Once again, if you start at 0 and 1, right? Let's go here. Because what does this tell you? 2 addition modulo 6, 3, sorry, 1 is equal to 3, which is true. Yeah, this edge is connecting 2 to 3. Okay, so it's very similar to what we saw over here. Now, for the same group, we know there is another generating set, right? Let's consider Z6 with the generating set 2, 3. Here we have only considered the generating set to contain that one element 1. Now let's go with the other generating set, which contains the elements 2 and 3. Right? So S also generates Z6. Okay. Now we have 2 elements. So for these elements in the generating set, we have to consider some type of edge. Elements in the generating set, right? For 2, I'll take the solid line. You have to give the arrowhead because the inverse of 2 is 4. For 3, I'll get this line with the dashed line without an arrow. Why is that? In this group, the inverse of 3 is itself, right? The inverse of 3 is itself. So we have these 2 elements. Now, we are starting with 0. Let's start with 0 over here. Right. Now we have 0 plus this this binary operation refers to addition modulo 6, right? So you can simply say 0 plus 3. 3 referring to this dash line, right? So 0 plus 3 is 3. Divide by 6, you take the remainder, you end up with 3. So through the dash line, you connect 0 to 3. On the other hand, corresponding to this solid line, we have to see, because for each vertex, like I told you, we must have these two lines, right? These two edges. 0 plus 2 gives you 2. 0 plus 2 is 2. Divide by 6, take the remainder, you get 2. So from 0, you have directed line to 2. Okay. Now let's go to 3. If we go to 3, we see 3, we want to see where the dash line go from 3. Okay. 3, this gives you what? 0, which is exactly what we would expect. Why? The inverse of 3 is itself. So you only have this one line segment, right? This edge would correspond to the element and its inverse. Whereas for this one, you must have an arrow in the other direction corresponding to the inverse, right? Now let's go with, for the solid line, we would find 2, this is simply 5. Right? 3 plus 2 is 5. Divide by 6, take the remainder, you have 5. So you have from 3 to 5. Now let's go to 2, right? We want to see where this dash line would go. 2 plus 3 gives you 5. So you have this connection, right? Then we see that to see where the solid line would start at 2 and go, right? This is equal to 4. So starting at 2, this solid line, it should go connect to 4, which I will put somewhere here. Okay, right. Go to 5 again. We see that 5 plus 2 is 7. Divide by 6, take the remainder, it's 1. So we must have 1 somewhere here. I'll put 1 here. From 5 to 1, this directed edge, right? And then 5 plus 3, you should get 2, right? Once again, why is that? Because this line has no arrowhead. The inverse of 3 is itself, right? 5 plus 3 is 8. Divide by 6, you take the remainder, which is 2. Exactly what we would expect. Right, now let's go to 1. 1 plus 2 is 3. So from here, we have this direct connection to 3. 1 plus 3 is 4. So we have this line segment, dotted line. Then we see for 4, 4 plus 2 is 6. So it's directly connected to 0. 4 plus 3 is 7. Divide by 6, take the remainder. You have 1, which is what is denoted by this line dotted line segment. This is the Cayley diagram for Z6 under this generating set. So you have two different diagrams for the same group. This is with respect to the two different generating sets. Is it clear to you how we got this one?
Yes, madam.
Okay, no problems. Right. Now we see several properties of these diagrams. One thing is it's connected. In each case, it has to be connected. Why is that? Because we would always have for any element in the generating set X, right? Any two vertices G and H, those would refer to elements that are in the group, right? G times X equals H will always have a solution, right? So they must be connected. There must be a way to go from one vertex to the other. There must be a path between any two vertices in the graph, right? Why do we have a path from any two vertices? Because in any case, the equation of the type gx equals h will have a solution, right? The x, g, h, they are all elements in the group. So the inverse exists. Take the inverse on both sides. You can always find a solution to x. On the other hand, uh, we have at most one edge going from a vertex G to a vertex H, right? Why is that it's at most one vertex? Now, in this case, we have one edge going from 0 to 1. There is no other edge going from 0 to 1, only one edge. This other edge that you see over here is coming towards 0. Between 0 and 1, exactly one edge. This is because the solution, now in this case, you see 0 plus 1 is equal to 1. The solution of this is unique. The solution of this is unique, gx. If there is a line connecting or an edge connecting G to H, you have a unique solution to this equation, okay? And then you take any vertex in this digraph, right? And you can have only one edge of each type starting at G and one edge of each type ending at G. Now, in this case, we only have one edge anyway. So if you go to this one, you have this type of edge and this dotted edge, right? If you go to 0, there is only one edge of this, one solid edge starting at 0, one solid edge ending at 0. Um, right. So this is what we call a Cayley diagram. Moving from here, the next topic to be discussed, groups of permutations. We already know one group of permutation. What is that? We have studied that one group of permutation already. What is that one group of permutation that we have studied so far?
Symmetric groups.
Which group?
Symmetric groups.
Yeah, the symmetric group. Exactly, right? S3 of order 6. That is one group of permutation. Now, we will learn another one, which is actually important and pops up in a lot of examples. The dihedral group Dn, right? Let me write, we already know one. S3. Now, today we will learn another group of permutation, the dihedral group Dn of order 2n. So let's write nth dihedral group Dn, and it has order 2n, right? It has order 2n. Okay, nth dihedral group Dn. It's of order 2n. So what sort of a group is this? This is the group of symmetries of a regular n-gon, right? Let me first write it and then I'll tell you what we mean by that. How do we find these symmetries? This is the group of symmetries of the regular n-gon, right? What do we mean by a symmetry? By a symmetry, we mean this. First, you take this n-gon, right? So it's a polygon of containing n sides, right? We have the triangle. In this case, we would consider the equilateral triangle. Then we have the square, the pentagon, hexagon. Likewise, we have all these polygons. If it is a triangle, what do we mean by a symmetry? We take the triangle, so we take this n-gon, and we take a copy of it. We want to move this copy on this polygon, and somehow you can move it any way that you like in the 3 space, right? So you can either, there are several ways to do this. You can either rotate it or flip it by an axis. And somehow, once you place it on top of the n-gon, this copy, it should completely cover the n-gon, right? It should completely cover this polygon. So for example, if you have a triangle, you take the triangle, uh, hold it at the center, right? Take another copy of the triangle, keep it on top of the original triangle, hold it at the center and rotate it, and see how far you've got to rotate it in order to place it right on this triangle, completely covering it, right? So this is one way to get a symmetry. So it's any motion of the polygon by taking a copy of it and moving it in any way in the 3 space, then placing it on the polygon to fully cover it, right? So you can either take rotations or reflections in through lines of symmetry, right? Through lines of symmetry, right? So we will be actually focusing more on D3 and D4, right? So let me write D3 is the group of symmetries of an equilateral triangle. Then D4 is the group of symmetries of a square. Right. Now let's first find the group D3, right? Let's find the elements in this group D3, the group of symmetries of an equilateral triangle. Let us denote by rho I rotations. Rho I will denote rotations. So we are actually rotating clockwise about the origin. So we'll be rotating clockwise about the origin, right? And then let's take, let me write it, rotating clockwise about the origin, right? Then let's take mu I to be reflection in bisectors of angles. We'll denote reflection in bisectors of angles, right? Okay. So what does it mean? Say we have the equivalent, suppose all these sides are the same size. Suppose this is the origin, right? And let's give, it's a triangle, right? So n is in this case 3. Let's give these vertices the labeling 1, 2, and 3. How do we get a rotation? We hold at the origin and rotate these so that once you start rotating it, at some point, it covers this triangle fully. So you keep a copy of this same thing on top of it, hold it at the triangle and rotate it until it covers the triangle completely, right? And how many different rotations can you take? You can actually rotate it until you start at this, get a copy, keep it on top of this, hold it at the origin. You can rotate it until you get one to here, in which case you will have the triangle fully covered, or until you get one to this point, once again fully covered, or this point, once again fully covered. Okay. Right? And how do we take the reflections? We take reflections in bisectors of angles. In other words, that is a line of symmetry, right? How do we bisect this angle over here? Those are of the same size, the angles. We take this line that goes from this vertex through the center. And suppose this is an equilateral triangle. You have this, right? Those are the bisectors, okay? So what do? We hold a copy of the triangle on top of this, and over this line, we take the reflection, sort of like flipping it, right? At that, so that would simply cover the triangle completely once again. Once again, you take the same copy, keep it over this, hold it at this line and flip it. Once again, you'll be covering, now assume this is, it has to be an equilateral triangle, right? Fully, completely covering the triangle. Once again, we do the same with this line. Okay, so how many different symmetries do we have? With respect to these three lines, we can get three symmetries. With respect to these rotations, once again, we can get three different rotations, right? How do we get three different rotations? First of all, you can keep the copy and not do anything. In that case, we are not rotating. It's a rotation about the origin by an angle 0 radian, right? In other words, not rotating at all, right? So that would refer to one symmetry if you leave it be. Then you take a copy of the triangle, keep on it, hold it at the origin and rotate it clockwise until you get this vertex 1 over to 2. Because it's an equilateral triangle, we see that would that one rotation by an angle of 2 pi over 3 radian, we would have 1 at 2, 2 at 3 and 3 at 1, completely covering the triangle. And another rotation, another different rotation would be if we take this rotated clockwise until we got 1 to 3. In that case, 1 would be over 3, 2 would be over 1, and 3 would be over 2. Once again, if we rotate it, we'll be back at the original spot. So those will be the three different rotations. Okay? Right. So how do we find these rotations? Let's write row 1 to be the first rotation. Yeah. 1, 2, 3. Let me put it this way, right? We have seen this notation when we were talking about S3. Not really a cycle decomposition, but in order to introduce this, we use this notation. Now, 1, 2, 3 over here, we want to see where we are going to permute these vertices, where we are going to permute these elements. Take the first rotation, you rotate it by an angle of 2 pi over 3. You send 1 to 2. So 1 will be sent to 2. 2 will be sent to 3. 3 will be sent to 1. This is one rotation, right? Another rotation would be if you permute, if you rotate this triangle by an angle of, now this rotation by an angle 2 pi over 3 by the origin, right? If we rotate it by doubling this angle, right? Rotation by an angle of 4 pi over 3. Then we actually send 1 to 3. 1 will be sent to 3. 2 will be sent to 1. And 3 will be sent to 2. Right? And if we triple this angle, we will be back at the origin. So we will be back at the original spot, if you will. 1 will be sent to 1, 2 will be sent to 2, and 3 will be sent to 3, sorry. So you can think of as rotating it all the way by an angle of 2 pi. In other words, simply taking no rotation, right? So that other permutation, I will take it to be, let's take it to be row 3, sending 1 to 1, 2 to 2, and 3 to 3. You can either think of it as taking no rotation at all or taking a rotation by an angle 2 pi. Or rotation by an angle 2 pi. This is what we call the identity of this group. It's a group of symmetries, right? So we will denote it simply by 1. Why is this the identity? Because all these elements are fixed. None of them are permuted, right? So that will be the identity. Now, if we look at the symmetry, the reflections, if we go to the reflections, Mi, denote the reflection in bisectors. So let me write it separately. You have this equilateral triangle. 1, 2, 3. This is, let's say this is the origin. This is one bisector. This is another. This is another, right? Let's take mu1 to be the reflection about this line of symmetry. So you hold a copy over this and reflect it over this line. So you sort of like flip it. In that case, we understand 1 will not change. 1 remains to be the same. 2, however, once you flip this, 2 will go in to the place of 3. 2 and 3 will swap their places. Mu1 will be this. Let's take mu2 then. Mu2, let's take it to be the reflection about this line. In this case, 2 will be fixed, 1 and 3 will be swapped, right? Let's take mu3 to be the line of reflection, reflection about this line. In that case, once again, we see 3 is fixed. These two will swap their places, right? So we understand now D3 is the group containing the elements 1, which is simply row 3, row 1, row 2, mu1, mu2, mu3, right? Right. Now our next step would be to find appropriate generators of this group. Okay, we see identity is this one. And this is a group of permutations. As we can see, these 3 elements are permuted in different ways, right? Each corresponding either to a rotation or a reflection about a line of symmetry. Okay?